Welcome to LearnControlSystems.com. Today we're going to talk about what feedback is exactly and how we create a transfer function. And we're going to focus on transfer functions and how they're actually created and the mathematical models that follow. And how these mathematical models, which are a gain called the transfer function, is just output over input. And we take a set point, we multiply it times the gain of the transfer function, and we have an output. And we're going to show that with proportional only feedback control, there is always an offset. You never reach your set point when there's a disturbance. Disturbances always exist. So let's get started on this, and we'll take a look at what a transfer function is and a little bit about frequency response and filters that may be on the exam as well. In this section, we'll show that proportional only control just stops the upset. It doesn't bring the process variable back to set point. And we'll prove this with math. Okay, this is an introduction to control theory. It's going to be very simple. There's no differential equations, no calculus. There's no Fourier transforms. We don't care about all that. We're keeping this very simple. And this is a course for a technician or the PE. And this is to give you an idea of what's happening with transforms so we can use them on the PE exam. Okay, everybody's pretty familiar with P and ID. So if we look at this image right here at the bottom, what we have is we have a level tank. It has a level transmitter to measure the level. It has the process variable that's sent out by the transmitter to the controller. The controller then sends out the manipulated variable to the valve to control the plant. Most people say that the output of the controller is the manipulated variable, but we're going to say that the control of the flow into the tank is the manipulated variable. This is disturbance. It's D. We'll show it as a lowercase d. And the disturbance could be due to fluctuations in upstream process, a speed of a pump, or a load upset. Same way we could have a disturbance draining the tank going to the next process due to an upset. It could draw more flow or less flow. And this causes a disturbance, which causes a change in the elevation of the level. Okay, the controller has a gain of K. We'll be using the gain of K for the controller. And the plant itself, the tank itself, the plant, whatever that would be, in this case a tank, will have a gain of G. And when we take our set point, here's our set point, SP, and we subtract our process variable, set point is a reference, and it's what we want the level to be. And the process variable is what the actual level is that's sent back. So we take our set point minus our process variable, and we have an error, and this error is proportional to the level. Say you had a set point of, say, 5 feet, and you're at 2 feet, that gives you an error of 3 feet. So we just take the gain of the controller times the error, and that equals the manipulated variable. Okay. Here's a typical model of a control loop, and this is what we're going to focus on. Rather than focus on a P and ID and an image of a tank and a valve and a level transmitter, we're going to focus on how these control loops actually work. If we just go straight through and come out with no feedback, that's called the forward path or open loop. But if we take the output and we feed it back into the controller, this is a comparator, and the comparator compares the process variable, which is Y, the output, to the set point, the input, which we're going to use as R. So we'll be using R as our set point in control theory, and Y as our output. We have an error that comes out as the difference is the error. Same thing we had right here, it's error. And this error equals the set point minus the process variable. This will be E. Then we have the controller. We'll be ignoring this control element, and we'll just have the controller is outputting a manipulated variable to control the process. And this process will have a disturbance coming into it. This process may have, in this case, like fluctuations in flow. If we were controlling the temperature, it'd be like the temperature of the tank. If it's hot outside, it puts more heat into the tank, so you have to cut the feed of the gas down or the steam down. Or if it's cool outside, it gets cool outside, it absorbs the heat out of the tank, so we have to open the valve up more and put more steam into it to heat it up. Okay, the comparator takes the set point and the process variable. Usually we're using negative feedback, so we subtract the process variable from the set point. And this is shown with a negative and a positive, like we showed up on the top. The comparator is inside the controller. The comparator is inside the PID controller itself. It's done in the math of the PID controller. We have an actuator. Then the manipulated variable goes out to our plant, and we have disturbances come into our plant. These disturbances add or subtract from the value we want out of the plant: flow, speed, temperature, and that's our output. And we feed it back through the sensor. So if it was temperature, the sensor would be like a thermocouple, and the feedback element would be like a transmitter, a temperature transmitter. On this level transmitter, we wouldn't really have a sensor. We just have a feedback element, which would be the pressure transmitter feeding back a level. Okay, in control theory, we're going to use this model right here. It all reduces down to this right here. We have a set point, R, which is typically used in control theory, R. We have Y as our output. Sometimes it's C, but we're going to use Y. And after it comes through the sensor, which has a gain of H, we have a closed loop feedback, and this is our process variable. So this is Y closed loop, but it is our process variable. Process variable just measures the output of Y. We check the difference of these, we compare them, plus for the R. Since this is negative feedback, we have a minus on the YCL. That gives us an error. We go into a controller. The controller has a gain of K. We use K to represent the gain of the controller. We have a manipulated variable, U, and then we have the plant, which has a gain, and we give it a gain of G. G represents our gain. Little d represents the disturbance coming into the plant, and of course, Y is our output. Now, it's a little hard to follow a level on a tank, so we're going to use something that everybody knows. We're going to use an automobile. And in this automobile, we'll have a disturbance, which is a slope. It'll have a plant, which is the engine and transmission. And then we'll have a controller, which is the gas pedal that you set the set point. First, we're going to look at open loop, and then we'll look at closed loop, where we use the accelerator pedal to set the controller, and the controller will take over. Now, this math is not hard, so everybody can handle it. It's just basic 8th grade addition, subtraction, multiplication, division, but you do have to have an introduction to college algebra. We're going to do a lot of algebra manipulation in here. And even for the PE exam, when we get into the Routh criterion, we have to have a good understanding of algebra to manipulate our variables. You should have an understanding of complex numbers. It's not real important, but it'd be useful to understand how complex numbers work as well. Okay, in our example, we're going to use proportional only control, and we're going to use an automobile as an example because everybody understands how a car works. And our disturbances will be slope, which is the rise in a road or the drop off in a road, a hill. And we'll see how this affects the output. and we'll compare open loop to closed loop control. Okay, most of us have heard about feedback control and feedback loops and control loops in a plant, but how does feedback control actually work, and what is it? Feedback control, we need to look at the open loop first to see what's happening in the feedback. And open loop just means that you have a process. In this case, we have an automobile. This would be your process or plant, and the plant is the automobile. And it has a controller that could be mechanical or electronic. And it also has a process, which is the engine and transmission, that uses energy to transfer this energy out to do work. And our output is Y. Well, in this case, we'll have R is our set point, desired speed. We'll have U is the manipulated variable, which is the output of the controller that goes to the plant. And we have the process plant. And then the engine transmission does work and puts an output, which is the actual speed. This is from the book, chapter 15, and from our book, CSE Exam Reference Manual, a practical study guide. Here's a model that's a little more explicit of how it works. And this is where we start developing transfer functions. A transfer function is strictly a mathematical model that is a gain of the system. And we have an input. We multiply that input times the gain of the system, and we get an output. So in this case, we have our controller would be our accelerator pedal. And we'd have a set point. So we'd push down the pedal to a desired set point. It has an output. And this output would be like, would output to the engine transmission. And on the engine, it would control the throttle angle of the gasoline carburetor valve or the injectors. Well, nothing's perfect. Nothing in the world is perfect. Everything has disturbances. Well, a disturbance could be like a temperature. You're trying to heat something up and it gets cold and it absorbs the heat out of it, or it gets hot and it puts more heat into it, or it could be a flow rate and the pressure of the system due to the pump speed fluctuates and the flow changes based on the fluctuation of pressure, and this pressure would be a disturbance. Well, when you're driving, an example, everyday example, is the slope of the road. So as the road gets higher and higher and higher, and it starts going up more and more and more, our car tends to slow down and slow down and slow down more. And if we're going down a hill, the disturbance adds to the output speed, and we'll go faster and faster and faster. So we create a model of this. And the controller mechanism, which is our accelerator pedal, has a gain of 1/10. It has a gain of 1/10. That means for the angle coming in, we get 1/10 output manipulated variable to our carburetor. And then we sum that with the disturbance from the road. And the road will have a disturbance called the slope, which is the slope is just a gain itself. And it's a run, output or input. So you have what they call the rise in the road, and they call it the rise run or the run rise sometimes. But it's the rise in Y in feet over the run, the length of the road. And you'll see these signs once in a while. And they'll say like a 1% slope or a 3% slope. And you'll see these 3% slopes, which are pretty steep for trucks to stop and the brakes can go out. So they give warning signs, 3% slope. Well, we put in 1, 2, 3, 10% slope here. So you got a really big hill, it may have a 10% slope. And then it has a gain when it goes into the model, it has a gain itself. In this case here, it'd be 0.5. It'd be 0.5 would be our gain. And we subtract this. This is what the negative stands for. We subtract this from our output, U, the manipulated variable. And then it goes into the gain of the engine transmission. And the engine and transmission has a gain of 10. And then we get an output speed. So we got an input speed coming in. We have our controller. We have a disturbance that affects the output. That output goes into the engine transmission, which would, in this case, would slow down the engine transmission. And we get an output speed, which is going to be, if there's no slope, our input and our output are the same. It would have a gain of, with no disturbance coming in, say 0 times 0.5 is 0, then we have, say, 55, a set point of 55 coming in. We have 55 times 1/10 times 10 would be 10 over 10 is 1, and our output would be 55 miles an hour with no disturbance. But as the disturbance comes in, as we get more slope, our speed slows down. So let's look at the mathematics behind this. Okay, U, which is our output, our manipulated variable. Now, this is not the output of the process. This is the output of the controller. So U equals R, our set point speed, times 1/10. The output of the system, the output of the plant, is U, the manipulated variable, minus 0.5 times W, the slope of the road. Then we have that times the gain of the plant. So this output, R times 1 over 10 would be, this would be K of the system. And this plant, this 10 here, would be like G, the gain of the plant. So this would be the gain of the controller and the gain of the plant. So if we take U and we substitute in what U is, R times 1 over 10, we get R times 1 over 10 is R over 10, minus 0.5 times the slope, W, all times the plant gain, 10. Multiply 10 through, and we get R minus 5W equals the plant output. So if we take this and we use this formula of R minus 5W equals our output, so we have an input of 55 miles an hour minus 5 with a slope of 0 gives us 55 miles an hour. But if we had a slope of 1, we'd have our slope times 1 is 5. We have R, our set point, is 55 minus our disturbance of 5 times 1 is 5, and we get a speed of 50 miles an hour. Now with a slope of 10%, which is quite a big slope, that'd be 10 feet rise in 100 feet. So our output here would be 5 miles an hour. We take 10 times 5 is 50, and we subtract it from our set point, and we get 55 minus 50 is 5 miles an hour. So open loop control is not desirable. It doesn't really give you very good control at all, and disturbance really upsets it. But if we use a feedback model, here we have a controller, we have our disturbance, and we have our plant. And we take the output of the plant, which is our speed of the automobile, and we feed that back into a comparator. And a comparator compares the difference of the set point speed you desire with the speed of the actual output, and it gives you an error. And this error can be multiplied times the controller gain. This would be K, and this would be the plant gain. This would be G. And this would be our disturbance, D. So if we take that same drawing, and here's our plant has a gain of 10, and our controller has a comparator, and it has a gain of 100. Now, when you get into really high gains in proportional only control, you tend to get oscillations. This is an example from the Powell and Franklin feedback control book. So we have a set point, 55 comes in, we find out what is our output, we subtract the output, and this is going to be a Y closed loop from R, we get an error, we multiply it times 100, we get an output, a manipulated variable U. Then we come into another summing block, and we add in our disturbance from our road, which is going to be W, slope in whole percent, times 0.5. We subtract that. So if we were going downhill, this would be a negative slope. And so this would be a negative minus a negative slope would give you a positive, and it would actually add. So going downhill would add to the speed, while going uphill subtracts from the speed. We multiply it all by 10, and we get an output. Okay, let's look at the formulas here. Okay, R is our desired reference speed. We've set that. Error is the set point error. U is the throttle angle in degrees, sets the engine speed. YCL is the actual closed loop speed of the automobile in miles per hour, and W is the road grade in percent. So let's look at the math. So first thing we do is we get an error, and it's a set point minus Y closed loop, the output. Okay. The process variable would represent the closed loop's output speed. So that's just R minus Y equals an error. Then we went into our controller. So the error goes into the controller, is multiplied by the gain of the controller. This would be KE, or error times K, the gain of the controller. And that gives you U output, which is your manipulated variable. Now, we substitute in for error what error is, R minus YCL. So U, the output of the controller, equals R minus YCL times 100. Okay? Now, YCL equals U minus 0.5 W. So our output is U minus 0.5 W times 10. So our output here is U, 0.5 times W is subtracted. We multiply it by 10, and we get our output. Okay, next thing we do. So we got to substitute in what is U. Well, U is the set point minus the output. R minus YCL times 100, the controller gain. So if we multiply our controller gain, we multiply R and take our controller gain, we're going to multiply the set point and the process variable, R and minus YCL times 100. And we get 100R minus 100 YCL. Then that's U. Then you subtract your disturbance, 0.5 W. So we subtract 0.5 W, and we take all this and multiply it times the gain of the plant. The engine and transmission has a gain of 10. If we multiply through by 10, we get 1,000 R, and 10 times 100 here gives us 1,000 closed loop, Y closed loop, and then 10 times 0.5 gives us 5 W. Okay. So now we have that Y output is 1,000 R, the set point, minus 1,000 YCL, and this is the process variable, which is the output. The process variable represents the output, minus 5W, the slope. So let's gather like terms. We got a YCL on this side, and we got a YCL on that side. So if we add a 1,000 YCL to both sides, we get 1,000 YCL plus YCL equals 1,000 R minus 5W. So we can add this up and have a YCL here. So this is what we can do is we put this in parentheses. I should have showed this step and I didn't show it. We put this in parentheses, okay? And from here, we can take a YCL out, and it becomes YCL times 1,000 plus 1. So that becomes 1,001 times YCL equals 1,000 R minus 5W. Divide both sides by 1,001. And we get YCL equals 1,000 R minus 5W over 1,001. So that's 1,000 times set point minus 5 times the disturbance slope divided by 1,001 equals our output speed. So the output speed equals 0.999. When we divide this, we get 0.999 times the set point minus divide by 1,001, 0.005W. We can just leave it in this form. You can just leave it in this form and use this. So let's go down and look at this. So, like we did with the open loop, let's do the closed loop now. All right. So we have a slope of 0 degrees. So that'd be 54. With the slope of the 0%, the set point is 55 miles an hour. The output of the process of the actual automobile is 54.945 miles per hour. With feedback control, there's always an offset. There's nothing perfect about feedback control. Feedback control with proportional only stops the upset. It doesn't correct the upset. There's always an error. When you have feedback control, you always have to have an error. If an error doesn't exist, you don't have feedback control. Okay, there's ways to correct for that. We can correct for that with the integral mode, which will take the error and we'll have a time for repeats per minute, and we'll repeat the error times the process gain and add that to the output plus the process gain. That's something important I like to say is, I wish I had done this another way like I normally do. This is 1,000 plus 1 times YCL, where 1, when you see the number 1,001 plus 1,000 plus 1, that plus 1 in your transfer function is the last output state. That is the last output state. Okay. So when we calculate this, if we put in 0.999 times R minus 0.005 times 0, this becomes 0, and we get 0.999 times the set point. 0.999 times the set point is 54.945 miles per hour. So 0.999 times 55 minus 0.005 times the slope of 0 gives us 54.945 miles an hour. So with proportional only control, we can't hit 55 miles an hour. We want 55. We set it to 55 when we set our set point, but we only drive at 54.945 miles per hour because there's always an offset with proportional control. There always has to be an error with feedback. All right, now let's look at it with a 1% slope. At a 1% slope, we drop down to 54.94 miles per hour. So if we go 0.999 times 55 miles an hour minus our disturbance of the slope, 0.005 times 1, we get 54.94 miles an hour. We only lost 0.005 miles an hour with a 1% slope. So this is really good control with closed loop feedback and proportional only control. This has an extremely high gain. If you have a lower gain, you'll have a more offset. You'll have more offset with a lower gain. So you'll drift away from the set point a little bit more with lower gain. This is pretty high gain. If we had a 5% slope, we get 54.92 miles per hour. So we take 0.999 times 55 minus the disturbance is 0.005 times 5, and we get 54.92 miles per hour. Now at a 10% slope, this is a pretty steep hill. Remember, that's 10 feet rise in 100 feet, and our output is still at 54.9 miles per hour. If we take 0.999 times 55 minus 0.005 times the 10% slope, we get 54.9 miles an hour. So feedback control gives us a really good what they call regulatory control. It's a regulatory control. It regulates the output, and it does a pretty good job. Now, to correct for these errors, we can add integral mode, and if we integrate the error in time, that would be ET, error times time, times 1 over the time in minutes. So right now we got cycles per minute is 1 over minutes. You take the reciprocal and you get frequency of time. So reciprocal of time is frequency, and frequency is, in this case, would be cycles per minute, and typically our inputs are either repeats per minute or minutes per repeat. And again, it just takes the error from what it is and what you're looking for, and it multiplies that times the gain, and then it adds that to the output if it hasn't reached the output. After, say, you got 1 repeat per minute, that means it'll repeat that error. It'll add that to the output. So you're going 54.9 miles per hour, and we had an error of here is 0.1 miles per hour. So it'll take that error, 0.1, and it'll multiply times the gain of 0.999 times our repeats per minute. And it'll repeat that every minute and keep adding that to the output. And no matter what the slope is, the slope gets worse or less, it'll either add it or subtract it from it until we reach exactly 55 miles an hour. Okay, we saw how the math works with proportional control, and we actually derived a transfer function, although it wasn't obvious. So I wanted to make the transfer function obvious. Again, we'll go through the same thing. Get E equals set point minus YCL is our error, where YCL was our process variable. It was a measurement. So if we had a sensor in the feedback loop, it would be H. And it would, if it has a gain other than 1, like 0.99 or 0.75, we'd actually multiply an H times YCL. But we're not going to do that here. We're going to ignore the transmitter and say it has a gain of 1. What we're doing is getting down to our familiar transfer function of kg over 1 plus kg and show how it's derived. After we do all this math, we never have to do it again. We just see the loop, and we say, when we see the loop up here, we just say this is K, this is disturbance, D, and this is G, the gain of the plant. And when we see this, we'll ignore the disturbance typically, which set it to 0, and we'll just say when we see this loop, it's just Kg over 1 plus Kg. And that's what we're showing right here. So we got U, the manipulated variable, is K times E. The output of the controller equals the gain of the controller times the error. So the output of the controller, U, equals K times substituting for E, set point minus process variable, YCL. So then, YCL, the output of the plant or the process, equals U, the manipulated variable, minus the disturbance times the gain of the plant. Now, in all this, if you want, you can just set this DG, this D, to 0 and ignore the disturbance, and all the DGs will drop out. Even down here, this will be 0, and 0 divided by 5 or 5,000 doesn't matter. It's still 0. But we'll come back to where we are. So now we had YCL equals U minus D times G, the gain of the plant or the process. Then YCL, we substitute in what is U. U is K times R and K times YCL. So we get K times R minus K YCL minus the disturbance all times the gain of the plant. Multiply through by the gain of the plant. We get YCL equals KGR minus KG YCL minus DG, the disturbance, times the gain. We'll add a KG YCL to both sides, and we get YCL plus KG YCL equals KGR minus disturbance times the gain. So let's put this in parentheses. We'll put this in parentheses right here. This YCL plus KG YCL, put it in parentheses and take a YCL out of it, and we get the familiar term 1 plus KG YCL times 1 plus KG in parentheses. Divide both sides by a 1 kg, 1 plus kg. So we get YCL equals KGR over 1 plus kg minus DG over 1 plus kg. All right, like I said, if we set our disturbance to 0, it goes to 0, and 0 divided by, say, 1,000, 100, it doesn't matter. It just equals 0, and this would go away. And then you'd see your familiar terms here. And this is where we said, now we know how this works. We can just look at this and say that kg plus 1 kg. So it's just R, the set point, times kg over 1 plus kg minus plus minus, I should have put a plus minus here, plus minus any disturbance. And that disturbance will be dg over 1 plus kg. And I want to also add that this plus right here could be a plus minus. This should have been a plus minus as well to show you this, because sometimes you have a positive feedback and sometimes you have a negative feedback. Typically you have a negative feedback, but sometimes you do have a positive feedback. And if you had a positive feedback, this would be a minus. This would be 1 minus kg. Okay, that's it. That's the transfer function. So as you saw, kg over 1 plus kg is our typical transfer function with no disturbance. Usually we don't show the disturbance. And that is strictly, when we see this, is K, the controller gain, times G, the plant gain. The disturbance goes away. They typically don't show the disturbance. And so it's just KG feedback loop is 1 plus. When you see a negative, you add a plus. When you see a positive, you add a minus. So this is 1 plus kg. That's kg over 1 plus kg. And we don't have to do all this math. Okay, we saw how to derive a transfer function. And we got our transfer function of kg over 1 plus kg. And we showed if we add a disturbance, that would be dg over 1 plus kg. Now, these are both just gains. All these are gains of our system. This is output over the input, and this is the disturbance over the input. It's just a gain. So when we originally did our math, we did it with a gain, a controller gain of 100 and a plant gain of 10. Well, a controller gain of 100 is pretty high, and it's pretty unrealistic. That was the example used in the book. Typically, you want to have a low gain or it's going to oscillate on you, especially when you have a disturbance or a set point change. So what we do is if we set this down to 5, a gain of 5, set the controller gain to 5, that'd be K, leave the plant gain at 10, and we redo this problem, you'll see we're not that far from offset. It does, like I said earlier, you'll get a little more offset from set point, but it won't be that far because it's closed loop feedback. Okay, so if we take our controller gain, 5, times our plant gain, 10, we get 50. And so that's 1, that's all over 1 plus 50, 5 times 10. We had our disturbance, we plug in for D here, 0.5 W for D, and our plant gain of 10. And that's over the input of the whole closed loop, which is 1 plus 50. So this becomes 10 times 0.5 is 5, says 5W over 51, and this becomes 50 over 51. So we get our set point times 50 over 51 minus our disturbance, 5W over 51, equals our output speed. So our set point speed times the gain of our system gives us our output speed. This all reduces to 0.98 times the set point, R, minus 0.098 times the disturbance slope, the slope in the road. So with a gain of 5, we have a speed of 53.9. We can't reach 55. We're shooting for a set point of 55, but with a gain of 5, we can only reach 53.9 miles per hour. And here's our math at a slope of 0. At a slope of 1, we get 53.802 miles per hour. Not bad. With a 5% slope, as 5 foot and 100 foot rise, we get 53.41 miles per hour. And with a 10% slope, that's 10 feet rise and 100 feet, that's a pretty steep hill, we reduce down to 52.92 miles per hour, almost 53 miles an hour. We're only 2 miles an hour off. We're only 2 miles an hour off of our set point, and our integral will take care of the rest of that. So as you see, closed loop feedback does a really good job, even with low gains. So a high gain doesn't make that much difference than a low gain in speed between a gain of 100 at a 10% slope and a gain of 5 at 10% slope. That's less than 1 mile an hour in speed. Okay, let's move on to frequency response and look at filters and see how that works. Okay, frequency response is how quickly something moves, like how quickly a valve will move, or how quickly a motor responds, or how quickly a tank level responds, or a flow level responds. And with this signal, process signal coming back that feeds us the signal of what the process variable is, typically there's noise in there. And we want to see how to remove this noise in our process variable. And we'll look at this in a fair amount of detail here. Okay, let's talk a little bit about frequency response and what frequency response is. When you have it's not necessarily just a frequency like a radio frequency. It has a frequency, it has an AC component, and it's going up and down, up and down, up and down, up and down. And it has a period to it too. So with this frequency, we're looking at disturbances. And if you've got like a pump that's spinning around and it's it's got a lot of pulsations, it's got veins inside the pump. As the pump spins, it accelerates the water, accelerates the water, accelerates the water, accelerates the water. If you got a compressor and it's compressing the air, it compresses it, compresses it, compresses it, and compresses it. And these make pulsations. And you can get these pulsations in your line. You can get other noise too. Splashing in a tank on a level. As the water comes in and hits the top, it splashes. So the level kind of oscillates a little bit. And it puts this little ripple of noise in your output signal of your process variable measurement. Okay, we may want to get rid of those noises. And this has to do with a frequency response. What is the frequency? Typically, your AC electric is 60 hertz at 60 cycles per second. That means you got a peak every 60 times in every second. Okay, if we had 1 hertz, we just have 1 peak every second. If we had 2 hertz, we'd have 2 peaks every second. And this is our frequency. Okay, when we're looking at frequencies, we have to look at radians. And it's called rads. Most people call it rads. Radians per second. Radians per second. And a radian is going around a circle. A radian equals 57.3 degrees. And when you go around a circle halfway, that's called pi. It's used so much, we use it. We have a symbol for that, and it's pi. Pi is 180 degrees. So pi radians, which is 3.1416 radians per 180 degrees, and per 360 is 2 pi, and that's 6.28 radians, which is 2.68 times 57.3 degrees. But we don't care about the degrees. We just care about we're spinning in a generator, generating a voltage, or we got an oscillation in the tank and it's going up and down, up and down, up and down, up and down. And as it goes up and down and you're measuring this in time, it looks like a sine wave. And so it generates a frequency in your process variable. Okay. So we put in what's called a low pass filter. And typically your transmitter has a low pass filter built into it. And you can select the time for a low pass filter if you want one. But a low pass filter is strictly a resistor comes in, and then you got a capacitor coming down to ground, and you got an output voltage. And this output voltage is proportional to the voltage across the capacitor. Because we measure all of our loads go to ground. So if we come on here and we put another resistor, and this resistor is the load, would be, say, the input to the controller signal as our air. So we bring our air into here, and then we'd have the air come out and go into the controller, and this will dampen high frequencies. And this is called a low pass filter because it passes low frequencies and it won't pass high frequencies. Now, I don't know if you've had electrical yet. We have a section on basic electricity for automation and process control. And this is for mechanical and chemical people who haven't had electrical. And it teaches the fundamentals of electricity and all the basics. So there's a link on the website, and there's a link on the YouTube page. I believe it's 9, something like that, is the video on YouTube. So what we're going to do is we're going to create a transfer function for this model to see how it works. And we're going to look how frequencies affect it and how these frequencies affect the voltage coming out based on the model of our transfer function. Remember, it's an input times some gain in the system gives you an output. That's all there is to it. So let's look at how this 1 plus 1 or ST is created and what it means. Okay, we got I equals voltage resistor over resistance of the voltage. Again, you should take electrical if you haven't had this. It may help you understand this. So when you take voltage divided by resistance, you get current. The current is proportional to the resistor and the flow through the resistor. It's just like trying to go through a crowd of people. If you got a bunch of people, you can't hardly flow. And if there's hardly any people, you can flow very easy. So I equals voltage in minus voltage out. So that was the voltage in minus the voltage out to our controller. divided by resistance. And the formula for current, which is a little beyond you if you haven't had electrical engineering, I equals the capacitance times the change in voltage out over what they call respect to, but over the change in time. So we substitute in this voltage drop divided by the resistance for amps. So this is what amps equals. We put this in there, and we get voltage in minus voltage out over R equals C dV out dt. Okay, multiply both sides by an R. And we get voltage in minus voltage out equals RC dV out dt. Well, RC is a time constant. You should know that resistance times capacitance equals a time constant. So that's a time constant. RC is a time constant. Your resistance times your capacitance, it forms a time. It's a natural exponential. And when you try to increase something, try to charge something up with energy, it typically takes 5 time constants to reach 99.999% of your output voltage. And it's called the time constant. Okay, from calculus, we'll know that S, and Laplace transform, S equals d dt. So this d dt, which is the derivative of the voltage, it says take the derivative of the voltage, take the change in output with respect to time. Well, this equals S. And S equals 2 pi frequency. It equals what's called J omega. J omega. J says it's an imaginary component, and omega says it's an angular frequency in radians. And we'll substitute in, if you have electrical, you'll find out how this works. You'll substitute in 2 pi f. So that's omega is 2 pi f. And f is your frequency. Like we said, 60 hertz, 1 hertz, 2 hertz. And 2 pi is the radians going around in a circle. So it's how many times you go around a circle in a second. Or with oscillations, remember the tank's going up and down. And as your manipulated variable comes out, it makes the splashing in the tank. And so your process variable is measuring your process, and it's measuring the output of the tank. And so in time, it's going up and down, up and down, up and down. And it looks like a C wave. It goes up and down, up and down, up and down. It's not flat DC out like most people think. It varies, and you get noise in it. So we get voltage in minus voltage out equals RCS, volts out. So we collect like terms, add a volt out to both sides. And we get voltage in equals voltage out plus RCS, voltage out. So with this in parentheses, and we take a voltage out of it, we get Vn equals 1 plus RCS, parenthesis, volt out. Okay? Because this is RCS times volt out. This is RCS times volt out. It's all one calculation, all one multiplication. So that becomes a volt out plus RCS, volt out. Put it in parentheses, take a volt out of the equation, and we get 1 plus RCS, volt out. If we take volt out, we multiply it times 1, we get volt out, and multiply volt out times RCS, we get the same equation. Now divide both sides by 1 plus RCS, and we get volt in over 1 plus RCS equals volt out. So you got divide both sides by volt in, and the volt ins cancel out here. We get volt out equals volt out over volt in here on the other side. And we get 1 over 1 plus RCS equals volt out over volt in. Well, this is a gain. This is output over input. So as you see, this is a pure gain. It's a pure gain. And T, time constant, equals RC. That's how much time does it take to get the 63.3% of your rated voltage in exponential growth. It's just a natural phenomena that it takes so long to go through the resistance and charge up that capacitance. Just like if I put a valve going into, put a valve in a pipe going into a tank, and I'm filling up the tank, the valve has a resistance to flow. The tank has a capacitance, which is the area of the bottom, and that's an RC time constant. And if we take that R times C, we get the time it takes to charge 63% of our level. So now we get this transfer function. All we got to do is just use it by multiplying Vn times both sides. And we get Vn, our voltage in, or signal in, times 1 over 1 plus S tau equals our voltage out. So what is this S tau? Well, that's, again, j omega. S is j omega, which is 2 pi f frequency. And when we multiply the j omega times t, if it equals 1, we get 1 plus 1 at the bottom, which is 2. And since it's j omega, if you've had your algebra and you've had your imaginary numbers, you know to add up an imaginary number and a real number. This 1, the last output, is real, and this is the new input, which is imaginary. And so we have to take the square root of these, and we take 1 squared plus st squared square root, and that equals the number. That equals the complex number. And all we do, if it's 2, we take the square root of that. That's 1.14, and we take the reciprocal, and it's 0.707. So when this time constant times this frequency equals 1, we're at 0.707, or 70.7% of our voltage. And this is what we call the cutoff frequency. When that frequency times the time constant equals 1, it's what we call the cutoff frequency. And at resonance, 70.7% is the effective bandwidth. In other words, that is the effective bandwidth that you can use. So we're using 70.7%, and we call this minus 3 dB. So let's make a Bode plot. So this is the resistor we saw before is 1,000 ohms. And the capacitor is 2.65 microfarads. So that's 0.000000265 farads. All right. And our volts in is 10 volts. We're setting this F sub C, which is the corner frequency. This is the frequency at which you start attenuating to 70.7% of your voltage. We call it the corner or cutoff frequency. And we're doing this as house voltage, 60 hertz. So typically you want 60 hertz. This would be like, say you got a UPS and it's a 60 hertz UPS, and you got a 10K messenger signal riding on the voltage to communicate back and forth with electronics, and you want to filter that out. So you want to filter that out. So the time constant equals 1,000 ohms times 0.00000265 farads equals 0.00265 seconds. So your time in seconds is 1 over your frequency. So 1 over your frequency is your RC time constant. Now, sorry, your period of a frequency is just the reciprocal of the frequency. But the time constant is your total radians, 2 pi f. You take the reciprocal, and that's your time constant in seconds. So time constant is just R times C, and we get our seconds. And we get voltage in times 1 over the square root of 1 squared st squared, where S equals omega. It's j omega. It's an imaginary number. That's why we have to, it's a complex number. This is a complex number. So j omega, which makes it an imaginary, and it's a complex number, and that equals 2 pi f. So we just plug in 2 pi f for S. All right, then we got a system called dB, and dB stands for decibels. It was actually invented by the Bell Laboratories. And it says how much attenuation per decade does your signal have? And that signal would be 20 log voltage out over voltage in. So we take our voltage out, that's when we take our input times our frequency here, take the square root of it, times our time constant, and take the square root of that, add 1 to it, take the reciprocal, and we multiply it, and we get voltage out. So you take it voltage out or voltage in, you take the log of it and multiply it times 20. That gives you dB. Minus 3 dB is 70.7%, and that's your effective voltage. After that, you're starting to lose your control. You're starting to become unstable. It's attenuating too much to really say you have stability. Okay, so you can go into the book and look at this, and we've generated it for a frequency of 1, a frequency of 5. So here we get 1 would be 6.28 radians times a frequency of 1 gives you 6.28 radians. And then we multiply it times our time constant, which is 0.00265 seconds. We square that and then add 1 to it, take the square root and the reciprocal, multiply 10 times it, and we get our voltage out at 1 hertz is 9.9986 volts. So if you want to find out what your phase angle is, how much have you shifted your input compared to your output, that would be 6.28. It's your imaginary number, 6.28 times 0.00265 over your real number, and this is your real number, 1, over your real number. Take the inverse tangent, and you get you're at 0.95 degrees. Okay, let's just jump ahead. We saw how that works. Our dB is 20 log, our output voltage, 9.9986 volts over 10 volts, and we get minus 0.0012 dB. So as the frequency increases, you'll see that the dB keeps getting bigger. It drops more and more. At 10, we're at minus 1.187. So here we're closer to DC. We're closer to a DC low frequency coming in. And let's just scroll on up. Here are frequencies 50 hertz, and here's our corner frequency. And our corner frequency is 60 hertz. So when we look at our radians per second, that's 377. So 2 pi 6.28 times the frequency, 60 hertz, gives us 377 radians, times 0.00265, that equals 1. That's almost exactly 1. Square that, and we get 1 plus 1 is 2. Take the square root of that, we get 1.414. Take the reciprocal, and you get 0.707. 10 volts times 0.707 gives you 7.07 volts. So at our corner frequency, we're at 70.7% of our voltage. If we look at our dB, we got 7.07 volts over 10 volts. Take the log of that, and then multiply it times 20, and you get minus 3 dB. And minus 3 dB is what they call the corner cutoff frequency. And it's at 45 degrees. Take our imaginary number, and 377 times 0.0265 is practically 1. So for all circumstances, we'll say 1. And that's 1 over 1, and the inverse tangent of 1 over 1 is 45 degrees. Okay, we take all these calculations here, and we put them into a plot. We go clear up to 100,000, a frequency of 100,000 hertz, which is 6,200 628,000 radians per second, and you're at minus 84 dB. You're down to the frequency so high, and the capacitor looks like a short circuit. As the frequency increases, the capacitor looks more and more like a short circuit, and you're shorting out the voltage. The current just drains the ground, and you don't produce any voltage out to your load resistor, which is going to your controller for the signal. So your signal going to the controller is 0.0006009. Now, these frequencies, when you're really doing this, it isn't just one frequency. It's a complex frequency. It's made up of multiple frequencies. So the DC and the low frequency signals will come through, and the high frequencies will short the ground, and only low frequencies will come through, and we'll get rid of this noise that's riding. It actually rides on top of the low frequency noise. The high frequencies ride on top of the low frequency noise. And say you got a curve like this, and you got a high frequency noise that's riding on top of that, up and down, up and down, up and down, up and down. Well, it takes that high frequency, drains at the ground, lets this low frequency go through. This gives us a nice smooth process variable coming into our controller and our calculation, so the output isn't so jagged and it's smooth. But here's what they call the Bode plot. You won't need to understand the Bode plot for the exam. You may need to understand how to create a filter and understand, they say we got 5 hertz noise, and they want to know what size filter should they have on there. How many seconds should the time constant be to get rid of that noise? So you got to understand that you take your frequency times 2 pi, and then you take the reciprocal of that, and that's going to be your time constant, and that'll be the time constant you use for the filter. So they may have, I've had this on the exam before, so they may have that on the exam again. So all these voltages we just plotted, I plotted this voltage here, and we plot the dB versus the frequency. So here we're only going up to 62,800, which is 10,000 hertz. So at 1 hertz, we're practically right there. 5 hertz, we're practically there. 10 hertz, we dropped off a little bit. 50 hertz, we dropped off a little bit. And then we're at about 1.5 dB, 1.5 minus 1.5 dB here. And then at 60 hertz, we're at minus 3 dB. This means we're at 70.7% of our voltage. And as you see, the voltage just really drops off as the frequency increases. So we can't use this voltage after 3 dB. We don't want to use it because your system could become unstable. And here's a plot of the phase angle. So again, we'll plot our frequency. 1 is practically at, maybe at 1 degree, maybe less than 1 degree. And then at 5, we're at like 3 degrees phase shift. And then at 10, we're at 10 degrees phase shift. 50, we're at like about 41 degrees phase shift. And then at 60 degrees, we're at 45 degrees phase shift. Okay, so now we kind of understand what frequency response is and how we use that to filter. And, if we didn't get rid of these frequencies, our valves would be going up and down, 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 and they beat themselves to death. They wear out. You wear out the gland, the packing gland. You use up the air. You wear out your I to P because it's moving so much back and forth, and it tends to cause wear, and you have a lot of consumption of air. And your process is going up and down, up and down, up and down, which means it's probably going to be off spec. So you need to get rid of these frequencies and keep it as close as you can to a DC. It's not going to be perfect. As you'll see when we're tuning in the tuning video, it'll go up and down, up and down, up and down, but eventually it levels out, especially on a stable system. It pretty much levels out to DC. The valve will have some frequencies to it. Since I'm using a simulator on the tuning video, The tuning video doesn't really show a lot of noise. It doesn't show a lot of noise. In a real plant, you're going to have a lot of noise. That's about it. The main thing we want to say is that proportional band has an offset. It doesn't correct. It only stops the upset of the disturbance. And so that's about it. Watch the video on tuning, which is video 7M, Ziegler-Nicholas tuning, and you'll get more of an idea of what proportional is and how it responds and how it never corrects back to zero, your set point. It always has an offset. It always has an offset. That's about it. We'll take a quick look at block algebra manipulation. This is very useful on the PE exam. Almost every exam has some kind of block algebra manipulation where you have to simplify the block and usually create the transfer function for it as well. So you should pay attention to this. Okay, one last thing we want to do is talk about block algebra. On the exam, you'll probably have a problem where you have to take some kind of a transfer function model and simplify it to the simplest form you can, like we did earlier with the automobile. And in the book, under control systems, we have the block algebra. And this is the original block, and this is the equivalent block. And it gives you different scenarios of how to change these blocks. Like G1 times G2 is just what we did, G1, G2, or G2, G1. Here we've got a sum of X1 and X2, and we're taking it into G. All we have to do is take a G and move it over here and put a G down here, and it does the same thing. So this would be X1 times G plus X2 times G. On this one here, we've got X1 coming into G and X2 coming out, going back as a feedback. Well, if we don't want it, if we want to move this, we may have a need to move this. Say this is another input-output here, a closed loop inside this gain block. We might want to move this feedback back here and make it a closed loop feed block. Well, all you do is just move this X2 back here. And since it was multiplied by G, we just multiply it by G again, put a G down here and multiply it. Now here we have X1, and X1's feeding back, and we got G, and we want to move this G inside here, say for a closed loop feedback. We want to do G1, or say K times G, and move our G inside. Well, all you got to do is X1's going through G to get X2, and you got X1 coming back. So all you do is X1 through G, then here's X2 out, then pick up past here at X2 and divide by G. So when this goes through the feedback loop and comes back through, it'll be G over G, and it'll still be 1, and there'll be no gain in this. This will provide no gain besides the gain that's in the system. So there's a couple different examples here. Here we want to move G on the other side of X3. Then we got X2. Well, all we do is put a block in here and say 1 over G, and it says divide X2 by G, and it becomes, when X2 and X3 are multiplied, it just becomes G over G, and this X2 becomes a gain of 1, and X2 is not multiplied times G2, times G. Here's a typical feedback loop. We got X1 coming in, and we got G, we're coming out, we got H coming back, so this becomes G over 1 plus G, H. This is just what we did in our example. We did 1,000 over 1 plus 1,000, except this transmitter, the feedback loop, the sensor, the transmitter, had a gain to it. If it has a gain other than 1, we don't need h if it has a gain of 1. We would just cancel it out. But if we had a gain of 0.9 or 0.75 or 1.2, we would need that gain, so we'd put that in our transfer function block of g over 1 plus or minus g h. Well, that's about it. You can look at this and work some of these problems and see if you can simplify some block algebra. You'll probably have to do it on the exam. On the exam, you'll be asked to find the poles of an equation, and they do this by giving you an open loop or a forward path block diagram with the equations that have frequency response in them, and we have to calculate these and change this to a closed block model, a feedback model. So let's look at that, how to do it. Okay, we saw how a transfer function is built. We saw basically what frequency response is. On the exam, the PE exam, this won't be for CCSTs and CAPS. This will be for the PE CSE exam. They may, well, there's been almost every test that's been on there. Some people say they didn't have it, but most people say they've had it. And so let's go over this. They'll ask about the Routh stability criterion. Now, we're not going to cover the Routh stability criterion. That's where you take the poles and of a function and you plug it into an array and you find out if it's stable by if the first number is a 0 or a -1, it's unstable. Otherwise, you use that to find out what range of gains can you use and still be stable. And usually this is in a 2-part. And so I'll let you study the Routh criterion, how to set that up in the book yourself. But we'll go over basically what they're going to do here is say, we have they'll show you a model of a closed loop function. And it has a forward path or an open loop path of G times B, gain of the controller and gain of the plant. And they say, if the gain of the plant is K times S plus 3 over S times S plus 1, and the plant equals S plus 4 over S squared plus 6S plus 13, what is the closed loop transfer function? And this is the solution to it. What we do is we just multiply this times this, and this times this, and then we do what we do for a closed loop. You take the forward path, the open loop path, GP, and the closed loop function equals G times P over 1 plus G times P. Okay, well, let's see how to get this algebra to actually solve for this. Okay, so the controller has, you can put these fractions at A over B times C over D, and you get A times C over B times C, and that'll be 1 plus A times C over B times D. And so you don't want this fraction in there. You want to get it into a form that will have our solution in it. And this is the open loop solution. We're going to show how to come up with this in a minute. So what you do is you just multiply both sides. This is a 1 plus A times C over B times D. And notice this is AC over B times D. So we want to get rid of this B times D on the bottom. So all you do is just multiply the top by B times D. So a B times D times AC, and the BD's cancel out and you're left with AC. On the bottom here, the BD cancels out and you're left with AC. But you had a 1 over here. Don't forget this 1. So you got to multiply BD times 1 and you get BD. And this equation simplifies to A times C over B times D plus A times C. And when you plug in the values for the open loop, we're going to solve for this in a second. We plug this in and we do the same thing. So this will be the A times C. And this equation here will be the B times D equation. And so when we do this, it looks like this. A times B over C times D. A times C over B times D. And this is one plus A times C over B times D. And this will come down into an equation that looks like this. And we'll have it solved. So let's see how to solve this. Okay, if we look at the open loop, the forward path loop, that was A times C over B times D. So remember your controller gain. Here's your controller gain, G, and here's your plant gain, P. So you got to use your algebra and just multiply these together. So K times S plus 3 is KS plus 3K. Take a K times the S and a K times the 3, you get KS times 3K. You always want your S at the end. Keep your S at the end in your powers, because these are called, these S's, when you're looking at the top, it's called a zero, and when you're looking at the bottom, it's called a pole. And we're going to try to pull these poles out, and it's just the power of the pole. In other words, if it's 4S, it'd be a power of 1, so that's this value of 1. For a 3S, its value is 6. For a 2S, its value is 13. And then you'll add these together like terms, but we'll get to that in a second. So when you look at the bottom, we multiply S times S plus 1, and we get S squared plus S. Then we multiply that times the other. So this is the controller gain, G, this over this, and this is the plant gain, this over this. So we multiply these together. So you take KS times S, and you get KS squared, and then you take KS times 4, and you get 4KS. Then you go plus 3K times S is 3KS, and then 3K times 4 is 12K. Do the same thing at the bottom. S squared times S squared is S to the 4th. S squared times 6S is 6S cubed. S squared times 13 is 13S squared. So S squared times 13, 13S squared. Now you do the S and you multiply times everything in there. S times S squared is S to the 3rd. S times 6S is 6S squared. And S times 13 is 13S. Now you do is gather like terms. So here we got an S squared, then we got a KS and a KS and a 12. So since these are the same, this is 4 plus 3 is 7. So we had our 4 plus 3 KS, and we get 7 KS. The KS squared stays by itself. It's the only term in there. And the 12K is the only term in there. So it becomes KS squared plus 7KS plus 12K. Gather like terms on the bottom the same way. You got an S here, an S cubed here. S4 is by itself. It's the only S4 in here, so it's S to the 4th. Plus 6S cubed plus S cubed is 7S cubed. Then plus 13S squared, 6S squared is 19S squared. And then 13S is by itself. So the open loop or the forward path equation reduces to KS squared plus 7KS plus 12K over S to the 4th, 7S to the 3rd, 19S squared plus 13S. All right, so you remember, we take this, our forward path, our open loop path, and we make a closed loop path out of it. So that's our gain over 1 plus the gain. So this is the combined gain of the controller and the process over 1 plus the combined gain of the controller and the process. Well, here's our equation for the controller and the process. So we just bring it down here. We put it right here over 1 plus the gain of the process and controller. Now, we can't use this form. We need in a regular fraction, just, zeros over poles. So we take this bottom right here, that is the same, and we just multiply through by it. So there's our fractions in closed loop, and we want to eliminate the bottom here. So we just take this bottom and we just multiply through by it and multiply through by it. Well, when we multiply through by it, we see we get ks squared, 7ks plus 12k, there it is. And then these two are on top of each other. They're equal to 1. They cancel out. They're equal to 1, so they cancel out. Same way on the bottom. You got ks squared plus 7ks plus 12k, and this s to the fourth, 7s to the third, 19 plus 13s. Same way on the bottom, it cancels out. But you had a plus 1 here. Don't forget, you get this plus 1. You got a plus 1 and a plus 1 here. So you got to multiply this value times plus 1 also. So you have to take this value on the bottom. When you multiply through top and bottom, and these cancel out, but you get this value times plus 1, so 1 times all this. So it becomes 1 changes to parentheses here, s to the fourth, 7s to the third, 19s squared plus 13s. Then you got your plus what we had here, ks squared plus ks plus 12k. And these, remember, cancel out. So the closed loop equation looks like ks squared plus 7ks plus 12k over, collect like terms here, we got s to the fourth, 7 to the s7 to the third, 7s to the third, 19s squared, 13s, ks squared, 7ks, and 12k. Well, if you notice, the s squared is 19, and the s squared here is ks squared. You can't just say 19k because that's multiplying. These have to be added together. So what we do is we take a 19 and a k, and it's 19 plus k times. So it's 19 plus k times s squared. Remember, you can't multiply, and that's multiply. You're just adding these together. So this is 19 plus k s squared. Same way for 13s. We got 13s, and then we got 7ks. We can't put those together except plus. So it has to be 13 plus 7k in parentheses s, and then 12k by itself. And there's your solution. So the poles, this is the zeros on the top, and these are the poles on the bottom. So your poles equal s to the fourth plus 7s third plus parenthesis 19 plus k parenthesis s squared plus parenthesis 13 plus 7k parenthesis s plus 12k. And we'll use these to actually calculate the Routh. I'm not going to go through the Routh completely, but I'll show you what we're doing here. Here's the Routh. And this is your first s. You start with s to the n. So this would be s to the n, s to s minus 1, s minus 2, s to the nth minus 3. So our highest number, you start with the highest number first. And our highest number is 4, s to the fourth. Okay, so Then we go S to the third, S to the second, and S. And then you put in any number you have there. So if we're like here, it'd be above this, we'd be above this, and we just go down. So we take the first number out of this, if we can see it here. So we take this first number and we plug this in, and we'd be starting right here. We'd be starting with S to the fourth power. So that means we got 1, 2, 3, 4. 4 spaces over here. S to the fourth. We have 4 spaces. And what you do is you put in what S is. And this here has a value of 1. So you'd put in 1. Then you go to the next one and you skip it. And the next one is 19 plus K. So we put in 19 plus K. And then you skip one and you put in 12K. And you put in 12K. Then the next one down, you do the next. You do to the third. So that'd be 7. And then you skip and it'd be 13K. And we'll show you how to do that in the Routh Criterion. It's a little confusing. It may not be worth your time to solve this. It's pretty time consuming unless you're good at it. And it's only one question on the exam. So it may not be worth the time. But here's an example of how to check for stability. And just follow this and you use these numbers and what they are. So A0, A2, A4. So this would be 0 would be the first one. In this case, it would be 1. 2 would be 19 plus K. And then 4 would be the fourth one, would be 12K. And then 0. Then the next one's going to be A1. So that's going to be 7. And A3 would be 13 plus 7K. And then A5 doesn't exist. So it's just 0. Then to calculate these B's, B1, B2, and B3, you have to use these formulas down here. And you have to combine these in to plug them into it. So it takes a little work and it takes a little study. Just get the book, read through it if you want to learn how to do it. And there you go. And that's about it. I think we're done with our video. We'll move on to the next one. Bye. Be sure to purchase my book, Control Systems Exam Reference Manual, a practical study guide, now in the 4th edition. Go to https://isa.org/CSE reference to purchase the book.